Hello and welcome to the course Introduction to the Psychology of Language. I am Dr. Ark from IIT Kanpur and we are in the third week of this course. In this week we are going to talk about speech production and comprehension. This is the third lecture in the series where we are discussing speech production. In the last two lectures I talked to you about the Viva Plus model, that was Level's model for speech production, which kind of carves out the whole process from conceptualization to articulation into small mental processes, componential mental processes, and kind of tells us how each of these processes might be happening or how each of these things might be happening in a very systematic, sophisticatedly detailed way. Okay. In the last lecture I talked to you a little bit about some of the evidence and where these evidences are coming from, and what do these evidences in terms of speech errors, or say for example the tip of the tongue phenomena, or also from say for example normal participants doing the picture word interference task or the picture naming task, tell us about this speech production process. In today's lecture I will discuss with you an alternative model, a different way of thinking about the speech production process, and that is by using the spreading activation model of speech production, which was proposed by Dell in around 1986 I guess. Okay. So let us talk a little bit about that model as well. Now if you compare this, what we have seen in the earlier model, the Viva Plus basically is that model assumes a specific kind of flow of information as people go from activated concepts down towards the phonetic gestural score. Okay. In particular, what really is happening is that a strict feed forward pattern, step 1, then step 2, then step 3, then step 4, no feedback from 4 to 3 or 3 to 2 and something like that. So a model assumes a strict feed forward pattern of the activation of each of these stages, and there are no mutually inhibitory links between these particular representations at any given point. So this is one of the things. So according to the Viva Plus, production begins with a set of activated concepts which leads to the set of activated lemmas before phonological information can be activated, and one of these, and so before phonological information can be activated, one of the lemmas need to be selected, then you will go on to activate the phonological information for that specific lemma. So this is the flow of information there. Hence Viva Plus falls within the category of feed forward class of processing models, because information only moves in one direction in this model and the system does not allow feedback to happen. Okay. So lower levels in this chain will not be able to feedback or give information back to higher levels in the chain. So that is not happening, that is not happening in the Viva Plus model given by levels. Consequently, what happens is that lexemes may not feedback and influence the activation of lemmas, and lemmas may not feedback and influence the selection of concepts. Also, according to this account, semantic substitution basically would happen because a target concept activates related concepts as well, and sometimes the wrong lemma may be selected, and that is why the entire process. Alternative accounts, however, could offer different explanations for semantic substitutions. Let us look at this. For example, the Dell's spreading activation model or speech production differs from the Viva Plus model in saying that it proposes a different kind of information flow altogether. It proposes two things. In Dell's model, information is allowed to flow both in the forward and in the backwards direction. So there is feedback that is possible within this model. Secondly, in the spreading activation model that Dell proposes, activation is also allowed to cascade through the model. What does cascading mean? It is almost like a drip kind of a thing. So once there is activation in the first level, there can also be some dripping activation in the second level and some dripping activation in the third and the fourth levels. As soon as you see activity here, you can see some residual partial little bit of an activity in the lower levels as well. This is the cascaded model. In the levels model, once the activation is here, everything will get completed here, then only activation will come here, everything will get completed here, and then the third and then the fourth level. So in the spreading activation account, by contrast, what will happen is that as soon as activity begins at one level, activation starts to spread at the next level. Thus selection does not really necessarily occur at one level already. Maybe you selected something at the different level, maybe you selected something, you committed the mistake at the last level, something like that. The spreading activation model also assumes feedback between levels of representation. Say for example, if the lemma of cat gains some activation, it can feedback the concept layer and reinforce the activation of the concept of cat, in turn strengthening its own activation. If the phonological information associated with the pronunciation of cat, k, and t, it starts to get activated, it will feedback and reinforce the lemma of the cat, which will feedback and reinforce the concept of the cat. So this kind of feedback can be very helpful if you see encountering or putting out some of the activity of the competing concepts. We've talked in the last class about competing concepts. Okay, so you you're looking at a picture of the cat, but also the word that is written rat, and both of them are competing with each other. This kind of model probably gives you a way of saying that because cat started to get activated, cat received a lot of reinforcement upwards and then back downwards, that's why a rat could very easily be lost. Okay. Now, what are the implications of this kind of a model? Let us look at it. Proposing that information flows both forwards and backwards through the language production system and in a cascaded manner, it could help us to explain a number of different things that happen when people speak. One of the things that can be explained from this is basically you could say that feedback connections from phonological processes to the lemma level, they help explain the lexical bias effect. A lexical bias effect is that out of all the speech errors that you would produce, sound exchanges or word exchanges, you're more likely to produce actual words as part of speech errors as compared to nonsensical words. In other words, you are more likely to do sound exchange on big feet as compared to big horse, because fig and beat, when you do the sound exchange, are both words as compared to hig and boss, which are both non-words. Very rarely somebody would kind of do a sound exchange between big and horse. However, people will do fairly regularly the sound exchange between big feet. Okay. Now, why is this happening? So, speech errors really reflected random errors in the phonological units. There is no reason why there will be large amount of sound exchange errors that would result in an actual word being produced. Fig beat. If the errors were purely, so that's the assumption that if these errors were purely based on hiccups in the phonological input, then you could kind of create any kinds of errors. Okay, but what has been actually seen in the data is that real speech errors almost never violate phonotactic constraints. What is phonotactical knowledge? If you remember from the last chapter, phonotactical is the knowledge about canonical beginnings and endings of words in the language. So, for example, that there is no word called hig and boss. I mean, you know that this is not really a canonical word, and that's why it is less likely that you will come up with such a output as compared to fig and beat, because both of them are real words. Now, interactive spreading activation accounts basically help they try and explain this lexical bias effect by appealing to feed forward and feedback links between lemmas and phonological output mechanisms. Let us look how. This is the model. You can look at the top level there is semantics, then there is these words, and the words are coming from onsets, vowels and codas. So, onset, vowels and codas combined basically make syllables. Now, in this kind of model, phonological activation begins as soon as the lemmas are starting to get activated, but before a final lemma candidate has been chosen. As phonemes begin to be activated, they send feedback to the lemmas that they are connected to, increasing the activation of those lemmas. So, it's like as soon as this lemma you're kind of evaluating, the sounds are being evaluated as well, and they're kind of feeding back. Because real words have representations at the lemma level, they have a higher chance to get strengthened, but non-words do not have any representations at the lemma level, so they will not get strengthened. So, more often than not, you will end up not producing finally the non-words, but you have an equally likely chance of producing speech errors that will incidentally given word as an output. Okay, that's basically the thing that's happening. So, it is less likely that a non-word error will result, because any set of phonemes that would lead to a non-word being produced will not have enjoyed any reinforcing activation from the lemma level. Nothing goes back. Thus, on average, sets of phonemes that produce non-words will be activated less than the sets of phonemes that produce real words. That's basically how the lexical bias effect goes. Also, these interactive activation accounts, the ones given by Levelt, can also help explain mixed errors. What are mixed errors? In a mixed error, the word a person produces by mistake is related both semantically and phonologically to the intended word. Okay, so semantics wise and phonology wise, both relations are there. Let us say an example. So, a person is more likely to say lobster by mistake when they intend to say oyster than they are to say octopus. Lobster and oyster phonologically very similar, semantically very similar as well. Octopus and lobster may be semantically similar, but phonologically are not really similar. Okay, these type of mixed errors are found to occur more frequently than they should if this was happening in a purely random sense, as was the case in the lexical bias effect. How is this happening? Let us look in more detail. Spreading activation accounts of speech production view the relatively high likelihood of the mixed errors as resulting from, again, the cascaded flow of information, okay, feed forward and feedback connections. Thinking about oysters, let's look at in more detail how. More specifically, thinking about oysters will activate semantically related items such as lobsters and octopi, which will lead to an activation of the oyster lemma, but also the lobster lemma and the oyster and the octopus lemma. Activating the oyster, lobster and octopus lemmas will also feed forward the the activation of the sounds that make up those words. So the connection is going further down. But because the stir set of phonemes is being driven by both the lobster and the oyster, it receives a little bit of more juice, let us say, it receives a little bit of more strength, and so that is why in the eventual output you have a higher chance of producing, even if you are going to make a mistake, it's a higher chance that you will make a mistake which kind of ends with a stir as compared to octopus, the pus part, because this is receiving less activation as compared to stir, because stir is receiving activation from both lobster and oyster. That's basically what is happening. However, if there were no cascading activations, then either octopus or lobster should have had an equal chance of outcompeting the target at the conceptual and lemma layers, and there is no reason why mixed errors should be more common than any other kind of error. So this is basically the explanation. So Dell and colleagues basically interpret the relatively high frequency of mixed errors as being evidence of cascading activation, because activation at one level is also feeding down the activation at the lower levels. Now we have been talking about the lemma quite a bit. We have talked about the lemma with respect to levels model. We've talked a little bit about lemma with respect to the Dell's model as well. However, it has been seen in recent past, not really very recent though, that the lemma level has come under a lot of criticism from various accounts. Let us look at some of the criticism that has been leveled at the lemma theory. Why is lemma a bit of a problem? Now both the Viva Plus as I was saying and the spreading activation style models, they propose that language production processes tap into a level of representations which is lemma. Just to remind you, lemma had meaning information as well as syntax information. So lemma has been viewed as a pre-phonological mental representation that captures information about a word's meaning and also the information about how it can interact with the other words in the given representation. So that's the syntactical part. This theory accounts for a variety of phenomena including picture naming behaviors, speech errors, tip of the tongue experiences and so on. So it has been a very important conceptual tool, so to speak, which people have been using in speech production literature for a long time. However, Alfonso Caramazza argues that the lemma theory does not do a very good job of dealing with evidence from patients with brain damage. See, in psychology or any science which deals with behavior, one of the things that you will also have to do is, if you have to have a good theory, the good theory should hold with cases of neuropsychological deficits, brain injuries, brain damage, so on. So if you have this theory that this is how I produce speech, if somebody has brain damage, you have to have a corresponding deficiency in this sequence of steps. Lemma theory, Caramazza says, does not really match up very well if you start looking at evidences in speech production errors which come from brain damage patients. Let us look at this more closely. Caramazza says brain damage can lead to language production difficulties, and different types of brain damage can lead to different kinds of difficulties, different patterns of difficulties. That's all right. Caramazza begins with the observation that if lemma were a necessary level of representation for production, then brain damage that affects the set of lemma representations should have consistent effects for people's ability to produce language, whether they were speaking or writing. Okay, so if lemmas for a particular set of concepts is damaged, then I should not be able to invoke or produce those set of concepts if I am speaking or even if I am writing. Okay, so just pause it, listen it back and then move forward. If lemmas are thought to represent grammatical information associated with specific words, so if the lemmas are damaged, grammatical aspects of production both in writing, reading should be damaged. In fact, there are patients who have difficulty with just some types of words. Okay, so that is one source of evidence. Some patients have difficulty with content words but little difficulty with function words. Okay, so content words like these nouns and verbs, cat, table, Hannibal Lecter, so on and so forth, as compared to function words like articles and prepositions and so on. Now the lemma theory would explain that a patient like that who has some kind of brain damage, for that particular patient, lemmas for the content words are selectively damaged as compared to lemmas for the function words, something like that. But as Karamazov notes that there are patients who have the opposite patterns of deficits as well. So depending upon how they are producing the word. So they can say, for example, if they are writing, one pattern will appear, if they are speaking, another pattern will appear. Let's take an example. One pattern of problems can occur with speech while the opposite pattern can occur in written language within the same patient. So it could be that a given patient could have trouble with function words in writing but with content words in speaking. In speaking, function words is alright, in writing, content words is alright. How is this happening? If the lemma for content words were damaged, then the person should have difficulty in both writing and speaking the content words. If lemma for function words were damaged, person should have difficulty in both speaking and writing the content words. So that is where this problem is really coming in. If both processes tap into the same set of lemmas, it should not be possible, as I was saying, for this pattern of problems to appear. So that is what I was saying, if the spoken production problem for content words is based on the broken content lemmas, then they should manifest similarly in both modalities. This is one set of evidence. Further, there is evidence against the lemma hypothesis from the semantic substitution errors that the brain damaged patients do. Let's look more closely. Some patients, when they are asked to name pictures out loud, will consistently use the wrong word. One patient consistently said the word dish when they were asked to name the picture of the word cook. When the same patient was asked to write the name of the picture, she wrote folks. So you see, the pattern of the error is different. Okay, these errors were not random, and the patient consistently produced one word dish while speaking, while the other words folks while writing. So there's also, if the damage is of the same kind, the output, at least in the speech errors, should have been very similar. That is not the case. Now further, Karamazov proposes that the solution to the problem lies in giving two separate sources of word form information, one for spoken language, one for written language. He says there should be different sources of information for spoken versus for written language. So visual processing versus auditory processing. He also proposes that the grammatical information should be stored separately from lemma representations, as this can account for the different patterns of function word and content word deficits that we just saw. Now this is a little bit of a problem with the lemma, so that's why you will see that people have kind of stopped really using lemma as a concept in more recent theories of speech production and comprehension. Now this was all about production till we talked about Viva Plus and we talked about DELs. Now let us move on a little bit more closely into the articulation part, into the production part. This will be the last aspect of production. You see, you come from the top, from concepts, etc. You have the phonetic gestural score, then you have the articulation. Let us look at articulation in a bit more detail. Now obviously the ultimate goal of speech planning was to make speech muscles to move and produce sounds, that is articulation. To speak, we configure our vocal tract, which consists of everything from the vocal folds here upwards and outwards to our lips and noses. You know, all of this is part of the vocal tract. Articulation is also both the end point of speech planning and the production and the starting point for speech comprehension. That's also known, you know, that's where this feedback loop kind of helps us. Now there are some accounts of articulation that classify speech sounds according to the way the articulators move. The articulators include the lips, the tongue tip, the tongue body, the velum, which is the soft part in the back of your palate, the glottis, you know, all of this is your is your vocal tract. These different articulators can be moved semi-independently to perturb or to stop the flow of air coming out of the lungs. So for example, I have to say B, I am completely stopping the flow of air, versus I have to say Z, I am kind of letting air partially through the teeth and the the tongue. These disturbances of the smooth flow of air, they basically set up vibrations which are modified by the movement of the articulators, and this is what creates sound waves. So as compared to say B, it creates a different pattern of vibrations as compared to when I am saying D or T or S. Okay, so the constriction of the flow of air is kind of modified by the movement of these articulators and is then eventually producing different kinds of vibration patterns, different kinds of waves, let us say, that are coming out of the mouth. According to the articulatory phonology theory, a theory that attempts to describe how articulation really happens, the outcome of the speech planning process is a gestural score, is a sort of a program or an algorithm of how each of these things will move, which creates a contrastive gesture. So this basically creates a gestural score, which basically is a gestural score which creates a contrastive gesture, a gesture that creates a noticeable difference between the current speech signal and the other signals of the language. So the whole point is that each sound can be uniquely identified by its gestural score, so to speak, broadly. The gestural score, what does it do? It tells the articulators about how to move. More specifically, it tells the motor system a few things. What all? Let us say, to move this particular set of articulators. So, if for example, if you study phonetics in more detail, or if you study speech and hearing in some detail, therein you will come across which particular sound. Say for example, you have dentals, labiodentals, you have alveolars, etc. Sounds are classified by which articulators are moved in producing those sounds. That is one. Towards the location in the vocal tract where a constriction occurs, so where the flow of air was blocked, that's also one very important thing. With the specific degree of restriction, it was partially stopped or completely stopped. Say B is completely stopped versus T is partially stopped, and in a characteristic dynamic manner. So this basically is going to, so these are all mini instructions, so to speak. Again, I am kind of oversimplifying this, but the gestural score creates a set of mini instructions in order for the system to know how to produce these specific sounds. So that's basically the aim. The movement of the articulators produce a set of speech sounds that can be classified according to three things. First is the place of articulation, second is the manner of articulation, and third is whether this is voiced or unvoiced. What I will do is, I will also say, for example, in the reference section with the slides, add for you a couple of reference videos wherein all of these things have been very detailed, in a very detailed way described, and that will basically help you understand this in some more detail. It's probably outside the scope of this discussion, so that's why I'm not really going into a lot of detail about this, but I'll put some of the links of the videos that talk about place of articulation, manner of articulation, and voicing. Okay. Now moving further, also note that we do not really produce isolated phonemes. So we do not produce sounds in isolation. That is also something that happens. We produce whole gangs of them. When we're speaking a sentence, you're producing so many sounds one after the other. Okay, and with an average of about one phoneme every 100 milliseconds. So one phoneme is coming out as 1/10 of a second from my mouth. Because we produce so many phonemes in a very short period of time, we have to figure out ways moving from saying one sound to another sound. Okay, and the way we move from one sound to the other sound kind of has effect of one phoneme on the other and effect of one phoneme on the second phoneme on the third. So this interaction between phonemes also happen while we are speaking, and this probably could be different from different speakers, different from different languages. All of that is possible. All of those crazy kind of interactions are possible. And this phenomena of this interaction is referred to as co-articulation. We are kind of not speaking in isolation, we are co-articulating a lot of these sounds. So that is also something important. What is co-articulation? Let us just try and define this. Gestures from one phoneme overlap in time with the gestures from the preceding and the following phoneme. This is basically what will lead to co-articulation effects kind of coming up. Let us look at this in a little bit more detail. Co-articulation affects both the production and perception of speech. So the way you produce is also affected, and the way somebody hears it is also going to be affected if a phoneme is produced in combination with a following and a preceding phoneme. Okay, say for example, the words pool and pan. Pool and pan basically are basically the same phoneme, but per in ool is said with P and O, and then this is said with P and A. And if you look at the physical signatures and also how people listen to this, both of them kind of are slightly different than each other. Okay, so this is precise. So P changes in both of them. So for example, P in ool kind of comes out differently versus P in pan kind of comes out differently. That's basically a demonstration of how co-articulation kind of changes the way we speak, also probably changes the way somebody hears us speak. Okay, so this probably was the last point in the speech production lectures that I was planning to give. This is all about speech production, and this was the end of the third lecture of the week. In the remaining two lectures, I will talk to you about speech comprehension. Thank you.